Hello and welcome to the Philip J. Curry Dinosaur Museum Virtual Speaker Series, where we have paleontology guests call in for a presentation on science, fossils, and dinosaurs, and where the public will be able to ask questions both here at the museum and live on YouTube. First, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis peoples whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, Kat Schroeder will be presenting the influence of juvenile dinosaurs on community structure and diversity. Kat Schroeder is a PhD candidate studying paleomacroecology at the University of New Mexico. She completed her master's degree in biology at the University of New Mexico under the advisement of Dr. Felisa Smith. For her master's and PhD, Kat has been studying the effects of extreme size and growth on the community structure and diversity of non-avian dinosaurs. Her research projects have included large data analyses of the body size diversity of dinosaurs across spatial scales, including an examination of the role of juvenile megatheropods in the structuring of dinosaur body size. She has also examined the evolution of skull structure in tyrannosauroids and microscopic tooth wear in tyrannosaurids through ontogeny in hope of elucidating the dietary ecology of these long extinct animals. Thank you for joining us today, Kat. And with that, I will let you take it away.
All righty. Can you guys hear me all right? Yes, no, maybe?
Yeah, we can hear you.
Okay, great. And you guys can see my screen and hopefully see me. So let me know if anything goes wrong. We'll try and get through this. So yeah, I am Kat Schroeder. I'm happy to be here today. Thank you very much for having me. And this is a fun, long presentation, so we'll jump right into kind of an overview of what we're going to be looking at today. So just as a quick roadmap, we'll start with a bit of an intro on some modern ecology, specifically why body size is such an important trait for animals. We'll discuss a little bit of what we know about global body size distributions of modern vertebrates so that you guys kind of have a roadmap, an understanding of what we see and what we kind of expected from modern ecology. And then we'll compare that with non-avian dinosaurs. And so for the rest of this presentation, when I say dinosaurs, I am referring to non-avian. So no birds for this demonstration or talk. And then after we talk about that, we'll discuss a little bit of the effect of taphonomy on the fossil record and how that applies to body size. That will bring us to our first question regarding what local scale or small scale body size distributions of dinosaurs look like and what they tell us about dinosaur ecology. We'll then look at the potential drivers behind dinosaur diversity and specifically focus on ontogeny, which is how animals grow, how they change through growth. We'll do a quick sum up of what we found, and then talk about some leftover burning questions that remain to be answered, and take a look at some of the work that's being done on those questions by me and by others. Hopefully after that, we'll have some time for some questions. And so now that we kind of know where we're going, let's get the show on the road. So like I said, let's start with some modern ecology. So George Bartholomew, who is the academic great grandfather of every ornithologist in the US, noted that the most important attribute of any animal is its body size. And that's because body size is proportionately related to just a huge variety of physiological and ecological traits, from things like range size to metabolism, energy flux, generation time, clutch size, all of these different things. And a lot of these co-varying traits are things that we can't really measure in the fossil record. So things that, animals that we only know through bones, we don't have the opportunity to measure their metabolism in the field. So understanding proxies for those things, like body size, is a really important thing to do if we want to understand more about the ecology of dinosaurs. So what exactly do we know about dinosaur body size? Well, in 2012, O'Gorman and Hone did a really great job looking at a global sampling of dinosaurs. So this is all not all of the dinosaurs, but a solid representation of dinosaurs from all across the world, not really picking any specific place, just everywhere, right? And they found that there was a really weird kind of distribution. Dinosaurs show this left skew. And what that means is that the majority of dinosaur diversity is centered around animals that are large. Big dinosaurs are more common. And that's really weird because what we know of modern birds and reptiles and mammals is that they all tend to skew in the exact opposite direction. They are all right skewed. So that means that most modern terrestrial vertebrates have their highest diversity in small body sizes. And that makes sense, right? Because the smaller you are, the less room you need, the less food you need. You can physically pack more mice into a room than elephants into a room, right? So ecosystems work the same way. In this, we really kind of expect to see this energetically. So the other thing that we note about global dinosaur diversity is that it's weirdly low. They're very much non-speciose. So when we look at modern vertebrates, we tend to see that they are in the thousands to tens of thousands of species. So there's about 10,000 birds, little over 10,000 modern reptiles, somewhere between 7,000 and 10,000 modern mammals. But weirdly, dinosaurs, non-avian dinosaurs, are only, they're barely scratching about 2,000 in the species count. And that's despite the fact that they are the dominant form of life, or vertebrate life, on the planet for 150 million years. So at this point, looking at this data, we start to kind of ask ourselves, what's going on? Why is dinosaur diversity so low? And why do they have that kind of backwards body size distribution where most dinosaurs are big? So the first thing we have to do, we have to take a step back and address the fact that when we study non-avian dinosaurs, we're looking at a limited data set. They're extinct, the fossil record is not perfect, and not everything fossilizes. So Caleb Brown et al. Did a really fantastic job showing that, in fact, small dinosaur taxa, particularly those below about 60 kilograms, are really underrepresented in the fossil record. They're kind of missing. And he emphasized, he and his co-authors emphasized that taking into account things like collection bias and preservation bias is really, really important when we're looking at dinosaur diversity. So let's back up a little bit more and look at what exactly are those things. So preservation bias is the unequal fossilization of species or individuals in a species, right? So Kay Berensmeyer has done a really fantastic job of examining preservation bias in modern animals, basically by looking at, when an animal dies on the African savanna and its skeleton is kind of left there, how long is it left there? Does it get destroyed? After a certain amount of time, what's really left, right? So what's getting preserved? And they showed that species on the African savanna that die, that have masses less than 100 kilograms, so about 200 pounds. Animals smaller than that are the ones that are most frequently transported, consumed, or otherwise destroyed. And they are therefore the least likely to become fossilized because they're getting destroyed before they can really get preserved. So remember that Brown et al. Found that dinosaurs under 60 kilograms were missing. Berensmeyer is finding that animals below 100 kilograms are missing. So this it makes sense about why we wouldn't necessarily find really small dinosaurs in the fossil record. The other one was collection bias. So collection bias tends to be a result of scientists going out in the field and kind of having a specific purpose about why we're going out and collecting. So if you're interested, for example, in finding the world's oldest dinosaur, you're unlikely to end up collecting a Tyrannosaurus rex, which was alive at the very end of the dinosaur reign. And as anybody who has read anything about the bone wars knows, a lot of paleontology was driven by museums that were really interested in having just the biggest and best dinosaurs. So between these two things, we have a dual problem, right? We have the issue that bigger dinosaurs are more likely to have been preserved in the first place, and they're more likely to have been collected. So that's some compelling evidence for why we might see this body size distribution in dinosaurs, right? But there's a problem with ascribing the entirety of dinosaurs' weird body size distribution to taphonomy. It's a problem that O'Gorman and Hone actually address in their 2012 paper. They note that in order for dinosaurs to look even like fossil mammals, we would have to be missing about 90% of all dinosaur diversity. And more importantly, all of that missing 90% of dinosaur diversity would have to be from dinosaurs that are smaller than 60 kilograms, right? In order to infill those small body sizes, we would just have to find pretty much nothing but small dinosaurs all the time, right? Which is problematic because we seem to keep finding giant dinosaurs. And when we look at things like Lagerstätten that do preserve really, really nicely and really small dinosaurs, we don't necessarily see a higher diversity of those small dinosaurs than we do in large dinosaurs in any other kind of formation. So while taxonomy and preservation and collection bias, they're incredibly important to understanding the diversity of dinosaurs, it's just not quite enough to explain what's going on with the entirety of dinosaur diversity. Specifically, there might be something going on that is more biological in nature. And so if we want to look at that kind of question, we need to look at scale, right? So quite helpfully from modern ecology, we know that when we look at global distributions like the one from O'Gorman and Hone, what we're really looking at are the effect of large scale drivers. So these are things like climate and plate tectonics, things that are acting on multiple species or between multiple groups of species over huge areas and over potentially a very long time. So conversely, if we want to look at ecology, we know that small scale distributions, so the local community distributions, are reflective of ecological drivers that happen because of the interactions between species or even between individuals within a species that are happening over small areas and relatively quickly. So importantly, we know that if the body size distributions of dinosaurs at the small scale, at the local scale, don't look like the global distribution, we know that there's a pretty good chance that there's something going on ecologically that's causing that difference. So this brings us to our first real question. So we know what dinosaur body size looks like at a global scale, but what does it really look like at those smaller scales? What does it look like in a community? And we predict, because we think that it's ecological in nature, we predict that dinosaur mass distributions at the local level aren't going to mirror their global distribution. The small scale is going to look different from that big scale because we think that something biological is going on. So to answer the question, we actually need to look at a bunch of local communities and see what their distributions actually look like. So this is a fairly complex problem, right? So fortunately, we have this amazing resource, the PBDB, the Paleobiology Database. So we went to the PBDB and compiled 43 different communities from all 7 continents, a variety of biomes, because we want to take out as much contributing factors as we can. We want to be as random as possible with this. Looked at a bunch of biomes from different latitudes. Our communities all together covered or contained over 550 dinosaur species. So we're looking at a fairly good sampling. And as amazing as the PBDB is, it should be noted that while the PBDB is a fantastic resource, we by no means just simply downloaded data and started playing with it, right? We had to build a clean data set first. So what that means is removing synonymous taxa, making sure that T-Rex and Dryptosaurus aren't in the same place because Dryptosaurus is really T-Rex in those areas, right? And then double checking everything against the most current literature to make sure that, you know, this animal is still really a dinosaur. It's not some synonym of another dinosaur, just to make sure that we're actually looking at real animals, right? On top of that, we did not include ichnotaxa, and there's some specific reasons around that, majorly because it's really, really hard to figure out diet for ichnotaxa. If you are interested, Martin Lockley and Lita Xing have since looked at ichnotaxa in a very similar kind of project. The citation for that is at the end of the presentation, but that has also been done with ichnotaxa. So after we start to clean up a little bit, We then took all of our communities and limited them as much as we could to biostratigraphic zones, so faunal assemblages. These are areas within a formation that we know the animals were probably in the same area at the same time. We're not just relying on the skeletons that are in a formation, because some formations span very, very long periods of time, and you can't really guarantee that each species in there is interacting with one another. So this, as a byproduct, which is a nice byproduct, this also limits time averaging. So you're not looking across the entire formation. And it basically, it really helps to ensure that we are actually looking at collections of interacting species, because that's in effect what a community is. And then everything left, so all of the species that were left in our formations, we then took mass from published estimates, and anybody that has looked at dinosaur mass knows that it is just a wild, wild ride, depending upon what kind of method you're looking at. So to avoid those differences in estimation techniques, we used averages of multiple masses wherever we could. Any taxa known to say the family or higher, and that should be mentioned, we did do this at the generic or specific level wherever we could. We didn't use anything that wasn't known more specifically than family, but anything that used to have a species name but then was kind of reclassified as it's probably a thing, but we don't know what a thing it is. Those guys, we collected as much information about their actual size. We didn't just jump to the family size. That said, all of our analyses use log 10 scale. It's a pretty common way of looking at things that have a huge variety in range. And yeah, so all of the dinosaurs in the communities were then, once they had mass and once we were pretty certain they were a real thing and in the community, we assigned a fairly basic trophic determination, so diet, right? For the remainder of this presentation, anything in blue is going to be referring to herbivores and yellow is going to be referring to carnivores. And we do use a little bit of shorthand, a little bit. Well, most theropod dinosaurs are carnivorous. Not all theropods are carnivorous. We do use that as a shorthand. But when I say carnivorous theropods, or specifically megatheropods, we are not referring to things like therizinosaurs or ornithomimosaurs. Those have been coded as herbivores, and we're not necessarily referring to those. So, and then of course we have the super enigmatic theropods like canignathids, which are just, yeah, guys, figure that out, because dietary information for canignathids is just, eh? We, generally speaking, when in doubt, we erred on the side of carnivores. So all in all, we feel that our dietary assessment is pretty accurate, but there's always those guys that may or may not be a little bit inaccurate in our data. So anyways, once we had all of that information collected for all of our species, we could finally map out histograms of body size, which look a little bit like this. So we have here dinosaurs in log 10 mass bins or half mass bins, showing basically how many species within a community fall into a certain size category. So here we can see that we've got some herbivores in that 1,000 kilogram to 3,000 kilogram range, some carnivores in the smaller area. This is the Horseshoe Canyon, for example. Here's the Morrison Formation. So you can start to see that we can see kind of the shape of communities. And if you stick all 43 of our communities side by side, we can start to see the kind of average community shape, which we can then statistically compare to that global distribution from O'Gorman and Hone. So in fact, we did this against O'Gorman and Hone and against our own larger data set. And what we see is that the global and local distributions don't match. So we've lost that strong left skew of the global distribution. The average community shape has a distinctly bimodal distribution, so it's got those double peaks. And here we're looking at the local as the dotted line, the global as the solid line. We also find that the shape of community distributions are very, very similar across biomes. So this is telling us that it's not necessarily some kind of climatic factor. It is something that has to do with the animals that are in these communities specifically. Time averaging, species present, continent, none of those things seem to really have any difference. So communities are consistently similar to one another and consistently different from the global. That's really important because this basically answers our first question. So this shows us that there is a shared ecological driver that is affecting the shape of dinosaur mass distributions. Unfortunately, we still don't know what that driver is. So if we take a closer look at the community level distributions, if we break this down, so let's look at the herbivores first, right? We see that they retain a lot of that strong left skew. So the community distribution looks quite a bit like the global distribution. Mathematically, we find that they don't actually diverge very significantly at all. So we can see in the combined likelihood line that the 100 to 3,000 kilogram bins are being filled with regularity. Those large mass bins are being filled quite commonly. Relative high diversity is maintained even down into the 100 kilogram bins. And this makes sense, at least for herbivores, in the sense of gigantothermy, thermal inertia, and increased protective benefits from large size. So it kind of, there are ecological reasons why it kind of pays off to be big as an herbivore. There are a lot of questions about why herbivorous dinosaurs might not be small. That we won't get into here, but it is a very interesting question. The carnivores are a different kind of situation though. So when we look at the carnivores, we see where that bimodality comes from in that overall community set, right? Unlike the herbivores, carnivores actually have their highest diversity in small body sizes. So they're the exact opposite of the global distribution. They are fairly diverse below 60 kilograms. So carnivores in general just don't mirror their global distribution, and again, indicating that there's an ecological driver in their body mass distribution. So interestingly, the bias against small dinosaurs in the fossil record doesn't really appear to be affecting the carnivores at the local level. And then we have this really distinct gap, right? And this is the crux for the rest of the presentation. There is a super low diversity of carnivores between 100 and 1,000 kilograms. This is really weird, right? It's over the commonly cited threshold for size bias. Right? Remember, Berensmeyer was finding that in modern organisms, anything below 100 kilograms was kind of missing. Brown et al. Found that anything below 60 kilograms was kind of missing. This is actually above that. This is some fairly large animals that seem to consistently not be in dinosaur communities. In fact, we find this gap in approximately 86% of our communities. And just to give you a context, this isn't a small gap, 100 to 1,000 kilograms. If we were to apply a similar mass distribution, so if we were to take what carnivorous dinosaur mass distributions look like and apply it to a modern mammalian carnivore assemblage of a similar size, something like Kruger, we would actually lose all of the carnivorous mammals between the size of a bat-eared fox and a male African lion. So clearly, there's something going on here. This is a significant gap. It certainly can't be explained by size bias in the fossil record because it is above what we find as the bias in most instances. And when we do the math, actually, we do find that there is a significant correlation between the size of the gap and the size of the largest carnivore in the community. So there's something else going on here. This isn't just a byproduct of poor fossilization. We don't find the gap in communities that don't have carnivores over 1,000 kilograms. And that's where we get this term megatheropod, right? So when we're referring to megatheropods, we're not just talking about megatheropods because they're big. We're actually talking about them being megatheropods because they could actually be changing the actual structure of the community around them. This brings us to question 2, right? What is causing this persistent gap in carnivore communities? We see it in a majority of the communities. There seems to be some kind of interaction with the megatheropods, but we're not entirely certain what that interaction is. So interestingly, right, 2012, another great paper came out from Codron et al. And they were testing mathematically the potential for competition in dinosaurs through ontogeny or through growth, right? One of their predictions was the existence of a gap in the fossil record of dinosaurs between 100 and 1,000 kilograms due to the increased complexity of ontogeny in dinosaurs. So That was a lot of big words. That's a lot to unpack. So let's slow down for just a minute and discuss a bit about, why dinosaur ontogeny is weird. So first off, dinosaurs are oviparous. They lay eggs, right? And granted, anything that poops out a ball of bones and claws and teeth and feathers is a little bit weird, but dinosaurs in particular are weird because they're big, right? So because of gas exchange, eggs can only get so big. Eggs can only max out at about the size of a soccer ball, right? So even if you're an 80-ton sauropod as an adult, you're still starting out the size of a border collie when you hatch out of that egg. So there's some things that we know about animals, especially the few remaining big predatory egg-laying reptiles that we have today, like Komodo dragons. When there's big differences between the size of eggs and hatchlings versus the size of adults in a species, particularly in animals with little to no parental care, we know that the infants and the juveniles of those species tend to exist in very different ways in their communities, right? So by and large, these teeny tiny babies are not going to be physically capable of capturing the same prey that their adult conspecifics can. So adult Komodo dragons, which are 200 kilograms and fully terrestrial predators that are known to hunt and eat things the size of water buffalo as adults, as juveniles, Komodo dragons actually live in trees and eat bugs, right? They're hatched out of eggs about the size of a chicken egg. And from that point, it's just a mad scramble up to the nearest tree because mom is just as likely to eat you as she is to take care of you. So ecologically, the juveniles of Komodo dragons are very, very different animals, despite being part of the same species as the adults, right? And this is a phenomenon that is referred to as ontogenetic niche shift. So your niche is basically where you live in the ecosystem. So what you're eating, literally where you're living, when you're active, all kinds of different things that describe, what role an animal plays in their ecosystem. And then ontogeny, again, is just how you grow. So shifting your niche through your growth, right? And this is a really important thing because ontogenetic niche shift is actually a way to partition resources. So resources being food or space. And when you can partition your resources, you can reduce competition within your species, right? So for dinosaurs, which compared to mammals, they have the bare minimum of specialization when it comes to feeding mechanisms. They're mostly too big to partition their habit vertically like birds. We're not going to find a T-Rex in a tree anytime soon. Any form of resource partitioning for these animals is super, super important because they don't have a lot of the other ways that we see partitioning, especially dietary partitioning in modern mammals. And this is important because when a species or an individual of a species ends up in the same niche, where they're competing for the same food in the same place at the same time, competition tends to pick a winner, right? And over long enough periods of time, we might actually start to see something called competitive exclusion, where one species actually gets pushed out of an ecosystem because of competition from another. And here, once again, we see body size starting to come into play because the bigger you are, the faster you reach competitive exclusion. So now, if we go back to our second question about the carnivore gap, based on what we know about dinosaur physiology, that egg-laying behavior, we predict that it's actually the juveniles of those megatheropods. Remember, the gap was correlated with the size of megatheropods. We think it's the juveniles of those megatheropods inhabiting different niches as they grow that might actually be causing the gap. When we're looking, you have to remember that this is a point that confuses a lot of people. When we're talking about body size diversity, we are looking at the adult body size, right? So we don't actually count T-Rex until it's 6 tons. But T-Rex might be doing something different when it's 1 ton or 500 kilograms, right? So we're generally not looking at the juveniles. We're only looking at the adults. So what happens if we actually look at the juveniles and the adults at the same time? So how would we do this, right? We start with mass death assemblages, and these are really cool areas of the fossil record where a catastrophic event has happened, and it has kind of killed and buried a lot of animals all at the same time. It is effectively a snapshot in time of the community. And from these, we can get a really good understanding of how many of each age dinosaur there was in a community, how many infants, how many juveniles, how many subadults, adults. And we can figure that out based on lines of arrested growth, which they're effectively tree rings on dinosaur bones that we see them in crocodilians and birds, but it records how much an animal is growing per year, right? So from the data from mass death assemblages, we can tell that for megatheropods, there's probably a pretty strong neonate die-off. So think of like sea turtles getting picked off on the beach. The ones that survive them, once they hit a certain size, nothing is really messing with them until they reach sexual maturity. So megatheropods, things like T-Rex, Allosaurus, they're putting in a ton of energy into reaching reproductive age and then dying relatively shortly thereafter. These big animals are really not reaching senescence, right? So it's a very much live fast, die young kind of situation. The other important thing that we can tell from lines of arrested growth, and is, as the name implies, is growth rate, right? So we can see that megatheropods we're spending extended periods of time growing through their juvenile and subadult stages. In fact, most of their life is spent in that range. They don't spend a lot of time as infants or adults. But this doesn't actually tell us anything yet about juvenile megatheropods, right? It tells us about their growth rate and how much they're surviving. In order to really compare them, we need to figure out a way of actually, mathematically setting them equal to adults in ecological terms. So what we can do is take that survivorship, figure out how many animals are surviving past year 1, year 2, year 3, year 4, right? We can combine that with the growth rate. How big are you at any one year? Do you weigh 5 kilograms or 20 kilograms or 100 kilograms? We can combine those two things to get a thing called biomass, right? Biomass is just a calculation of how many there are multiplied by how much does each one weigh. So for example, if you had 10 30-pound toddlers, that would represent the same amount of biomass as a single 300-pound adult. So pretty simple math. But what we can take from those biomass estimates, and for this project, we happen to do this for 6 species of Tyrannosaurids and 4 species of Allosauroids. What we can do with the biomass is to set the juveniles of each of these species relative to their adults. So if we say that one adult is worth 1, right? If the juveniles represent 60% of the biomass of the entire species, then an adult would be 1 and a juvenile would be 1.5, right? So what we're effectively doing is treating juvenile megatheropods as their own morpho species, not as their own species. They're still the same species. T-Rex is still T-Rex, but the juveniles are being treated as their own kind of ecological entity. So sure enough, when we do this, not only does the majority of juvenile megatheropod biomass fall within that gap, the carnivore gap starts to get filled, but the juvenile biomass is actually proportional to at least 80% of the biomass of adults for the majority of species. So if you think Tyrannosaurus rex as an adult has an effect on its community, the juveniles definitely do as well, right? So with the juveniles added, the carnivore distributions start to resemble their global distributions a little bit more. We start to lose a little bit of that gap. So now what we have is independent verification based directly on abundances and growth rates from the fossil record of the very real influence that juvenile megatheropods would have had on their environment. Essentially, juvenile megatheropods would have had a similar amount of influence on their community as adults of the same species, and exerted that influence mostly within the 300 to 1,000 kilogram body size range. So that was a lot. Oh God, I flew through that in a half hour. So to sum up, what we did, we explored the distribution of body size at different geographical scales. And we found that local distributions, small scale distributions, don't match global distributions. This is an indicator that potential ecological drivers are having an effect on body size in dinosaurs. We looked at community distributions and found that carnivores specifically have the largest disparity from the global pattern, with a consistent gap in the 100 to 1,000 kilogram body size range, and that precisely matches a gap that was predicted by ontogenetic niche shift and competitive exclusion. And then finally, we looked at juvenile megatheropods and found that they would have wielded significant energetic and competitive influence over their communities. So this is really important, right? Because the influence of those juveniles, the influence that they exert over their environment will affect everything from energetic studies to biodiversity to extinction and speciation. So if we really want to understand distributions of dinosaurs, we need to take into account the fact that these guys are not physiologically similar to mammals. They're probably not taking care of their young very much. They're egg laying. There's huge disparities in size between juveniles and adults. With some of these animals, particularly looking at Tyrannosaurs, there's huge morphological disparities between infants and adults. So we should be taking into account the juveniles of these animals when we're looking at dinosaur ecology. So that's cool, but now what, right? Where do we go from here? Well, there are some leftover burning questions from this work that I think are still awaiting answers. For example, the Carnivore Gap exists both in the Jurassic and the Cretaceous. It's persistent at least, but it's not stable, right? It grows significantly through time. The Jurassic body size gap is on the order of 400 kilograms. In the Cretaceous, that balloons out to almost 3,000 kilograms of space that is not being filled by any kind of carnivore that we know of, right? Because there's, at that point, crocodilians are predominantly aquatic. There's no mammals in the Cretaceous that are getting bigger than the size of a raccoon, give or take. There's really nothing to infill this body size niche. So what is it about the Cretaceous that it seems to be amplifying the gap? Well, recall that there was some pretty solid diversity among small carnivorous dinosaurs, right? This spike in small carnivore diversity might actually be attributable to the rapid diversification of Maniraptorans, the raptors, right? And Resende et al. Demonstrated that some of these raptors at least might have been developing endothermy, so warm-bloodedness. And that would have allowed them to really get on the same level of competing with like small mammals, right? Small mammals, birds, very, very active animals. It might have given them a competitive edge against other dinosaurs. And it would almost certainly would have increased competitive pressure at the low end of the carnivorous dinosaur body size scale. So with these guys here, what's going to happen is that it's going to be very, very difficult to compete as a small juvenile dinosaur and really, really hard to compete as a small adult carnivore, right? The other thing is that the Cretaceous is when Tyrannosaurs become proper megatheropods, right? These guys start off fairly small, and they just balloon throughout the mid to end Cretaceous. And Thomas Holtz really recently put out a paper exploring that how Tyrannosaurs, specifically Tyrannosaurs, they might have not just been using ontogenetic niche shift to take over medium-sized carnivore niches. They might have actually been taking over the adult megatheropod niches, which is really cool. And it would take a huge step to explaining why in the Cretaceous of Laramidia, we don't see any other large carnivorous dinosaurs other than Tyrannosaurs, right? And even in the south in the Cretaceous, we really predominantly see Abelosaurs. So there's something going on specifically in the Cretaceous that might be tied to tyrant dinosaurs. There's also a really, really interesting, huge faunal turnover, specifically in herbivores from the Jurassic to the Cretaceous. So the Jurassic is kind of filled with the giant sauropod dinosaurs. It is the age of giants. And a lot of that diversity at the end of the Jurassic is replaced by diversity in large still, but much smaller hadrosaurs, ceratopsians, pachycephalosaurs, other types of ornithischian herbivores, right? So if there are Jurassic megatheropods that are relying on those immense sauropod food sources, or if there were megatheropods in the Jurassic that were morphologically specialized to consume sauropods, that faunal turnover at the end of the Jurassic might have put them under immense pressure, having to suddenly compete with smaller theropods for food, suddenly lacking their favorite kind of food source, and realistically just lacking a lot of energy that, imagine the carcass of a sauropod. That is food for days. You think of whale carcasses floating to the bottom of the oceans, and it literally feeds an entire ecosystem. Sauropods would have been the terrestrial equivalent to that in the Jurassic. So this brings us to some new questions. So questions like, how did tyrannosaurs assimilate the niches of other megatheropods? Maybe they were better at shifting their niche through ontogeny. Remember that we know that tyrannosaurs specifically have a huge amount of morphological disparity from juveniles to adults. If they were just better at shifting their niche, they would have decreased their intra-specific competition. So that's competition within their species. And that would have given them potentially a leg up in dominating these ecosystems. Or alternatively, maybe their growth pattern is actually a byproduct of already having specialized morphology that favored them following that faunal turnover. We know that even before Tyrannosaurs started to get big, even before they were really the kind of monsters that T-Rex was, they actually had a lot of specialized morphology in their skulls, in their ears, in their sinuses that was already building towards that kind of bone-crunching, really robust morphology that we see in crowned Tyrannosaurids. So a way of addressing both of those questions would be to look at the stability of the megatheropod niche over time. So what role are megatheropods playing in the Jurassic? Is that different from the role that they play in the Cretaceous? And then specifically look at how the juveniles of those megatheropods compare against the adults of different species. Are the juveniles of the megatheropods in the Jurassic closer in functional space or niche space to the adults? There's lots of questions about how exactly this niche assimilation might have happened. So this is actually a project that I am currently working on with some collaborators from the Smith Lab, where we're attempting to look at functional diversity. So instead of looking at just morphological diversity, we're actually taking a lot of that morphology and translating it using science from other authors that have shown, this morphology tends to relate to this function. We're actually going to take that function and compare how different the Jurassic and Cretaceous carnivores are, and try and take a look and see if juvenile megatheropods, where they compare functionally to adults of species of all sizes. So that includes, juvenile tyrannosaurs competing with dromaeosaurs? That would be an interesting question. I doubt it, but that's the kind of thing that we're looking at. So with that, flew through it a little bit, but I would like to very much thank all of my collaborators on the project and everybody that helped kind of formulate the way that we did this. I thank the PBDB for their fantastic data resources, and especially thank the Philip J. Curie Museum for inviting me to speak. And with that, I am happy to take any questions.
Yeah, thanks, Kat. That was a really interesting talk. And now we would like to open up to our question period. And we do have a question from Kala. Do you see any examples of this phenomenon during any other time period?
So yeah, like I mentioned, we actually see ontogenetic niche shift today in things like Komodo dragons. If you're referring specifically to the gap, I don't know. That is a good question, and it is realistically, it's something that I would expect to see in, say, Cenozoic Australia. So there's just ridiculously huge. It's effectively take a Komodo dragon and just scale it up by like 8 or 10. It's called megalania. It's just this giant reptile, and that was the predominant carnivore on the as far as reptiles go, and in Australia for a minute. I would expect to see something similar as far as a gap potentially in the carnivorous fauna in Australia in the Cenozoic because of that. Anywhere that you're really seeing a huge disparity in neonate versus adult size, we tend to see these kinds of interactions through ontogeny. So we see it actually a lot in fish. We see it in even smaller reptiles. So Komodo dragon happens to be the biggest one. We do see it in other smaller varanids. We see it a little bit in crocodilians. But yeah, dinosaurs, at least Jurassic and Cretaceous theropods, seem to really be exemplified in that way.
Okay, question from Anthony. You mentioned how taphonomic and collecting biases affect the fossil record, but how did you account for the biases in your data set? Specifically, how do you account for the geographic collecting bias towards North America?
Well, there isn't, so we did end up having to relook at this. And there is a small bias towards North America, but if you look at the availability of data, that's kind of just what you're left with. So unfortunately, the fossil record isn't perfect. And there does tend to be a little bit more known about North American dinosaurs. That said, even when we remove quite a few North American communities, when we basically remove North America down to the same level as, say, Asia, we still see the exact same pattern. So it doesn't seem to be highly affected by the fact that there is somewhat a bias towards North American faunas. It's an interesting question, and I would love to see it delved into more as far as whether there is any kind of differentiation in continental distributions. The thing that I would say is that statistically, we did compare every single one of our communities against one another. And what we found is that statistically, the shape of each community, whether it's North American, South American, is not different, right? So it doesn't seem to matter mathematically that you know, this is North America versus South America. And that's part of the reason that we were actually led towards that inkling that it might be ecological, and it might specifically be something physiological with dinosaurs.
All right. Another question we have from Heathen Wizard. What is the relationship between growth rate, size, and niche shifts? Dr. Therian's work suggests a shift in diet for Albertosaurus, but they aren't growing anywhere near as quick as T-Rex.
Yeah, so that's a great question. It's something that still very much needs to be answered because we don't have a lot of fantastic evidence about, you know, interactions in the fossil record are very, very rare. We are very fortunate to have some fossil record of tooth interactions from juveniles of Tyrannosaurs, but they're not very common. This is yet again a question that really needs to be answered. We can look a lot at the functional morphology of jaws, doing things like FEA, and that tells us a lot about how dinosaurs might be eating or hunting. It doesn't necessarily tell us what they are eating or hunting. So we do have to kind of rely on those very, very rare kind of trace fossils where we're getting actual tooth on bone. Unfortunately, like I said, they're pretty rare. Another thing that I'm working on is DMTA, dental microarchitectural analysis, and this will hopefully tell us if the juveniles are consuming different parts of animals, if they are more active hunters than the adults maybe. But by and large, we really don't have an answer about exactly how is that, where are they shifting their niche, right? We can see maybe mathematically who they're competing with. We could look at that functionally as well. but it's really, really hard to get at those really specific dietary shifts. So we do know that at the very least within Tyrannosaurs, jaw morphology really points to them not having that bone crunching bite yet. They are developing it as an animal, you know, Jane size or smaller. And we do have some tooth feeding traces from animals like Albertosaurus that show that they were actually eating large hadrosaurs. The question is, did they catch the large hadrosaur, or are they being kleptoparasitic, or are they just kind of sneaking in and running out? There's a question about whether adult tyrannosaurs would tolerate smaller juveniles at a feed, right, if there was enough food. What we know about that from modern ecology is that large carnivorous animals don't actually have to eat the entirety of their meal. So when we look at particularly large reptiles, they might kill and consume part of something like a water buffalo, but not necessarily eat the entire thing. So there's a huge complexity to understanding the actual like specific dietary niche of dinosaurs. And we will probably never know exactly what it is, but it is a fascinating avenue for research. And I thoroughly encourage anybody that is interested in it to go after it and help us figure this out.
Another from Heathen Wizard. Do you see such a size gap within certain species? Like within just Hadrosaurus, would you see a certain age gap? Do you think they grow at a much faster rate than the more primitive members?
I think there were a couple questions in there. So to be clear, we don't see the gap in herbivores, right? So the gap that I'm talking about in this presentation is in carnivorous dinosaurs only. We might not see a gap for a few reasons, largely because carnivores have to be much more picky in what they consume. Large herbivorous dinosaurs, large herbivorous animals of any kind, have a capability because they're big and because they can support fermentation, right? They can support these vast gut floras that help them digest. They can consume really kind of crappy food, right? Carnivores can't, so the competitive pressure is already pushing more on carnivores. So we don't see the gap in herbivores. We wouldn't necessarily expect to see it, right? The other part of your question was about growth rate. And hadrosaurs specifically grow very, very quickly. And there's been some work done that has shown that there might be some kind of evolutionary arms race going on basically with the rate of growth in Cretaceous or Ornithischian herbivores related to the rate of growth of large Tyrannosaurs and Abelosaurs. Your question was a little bit vague, and I'm not sure if I got at what you were asking. So feel free to follow up with that, but hopefully that touched on it.
And a quick question from Kala. What would you like to study next?
Well, as I mentioned, I'm already working on a functional diversity project, which is a fascinating area of research. I think my favorite areas of research tend to be anywhere that I can take modern ecology and reapply it to the past. A lot of dinosaur paleontology in particular has focused on specifically on morphology and on phylogenetics, trying to figure out who's related to who and why do you look like this. I think there's a huge area of understanding that we're still lacking in as far as dinosaur behavior and you know, are they how precocious are dinosaurs as young? How gregarious are they? Do they move in herds? I mean, we know that at least for some herbivorous dinosaurs, we have no idea what juveniles of carnivores are really doing as young species. There's an immense amount of knowledge that can be gained. We're still not even sure what the metabolism of dinosaurs looks like. So yeah, anything that is surrounding really understanding dinosaurs as animals as opposed to understanding them as rocks, right? That's the stuff that really fascinates me. So right now I'm working on, as I mentioned, the functional diversity paper, another paper on dental microarchitectural analysis to try and really hone in on the difference in diet between juvenile and adult tyrannosaurs. And from there, it's you know, whatever question pops up next.
Okay. I'll ask another question. What's your favorite theropod?
You know, I think every adult complains that like nobody asks them what their favorite dinosaur is anymore. And as a paleontologist, that's one of the questions that I get asked the most. And honestly, like I have different categories of favorite theropod because there's just, I mean, Therizinosaurs are crazy animals. They're the dinosaur equivalent of giant sloths, we think. They're 20 feet tall and covered in feathers. They are the nightmare big bird of the Cretaceous. Like they're fantastic. As far as carnivorous theropods, everyone always expects me to say T-Rex. It's really not. He's overrated. He's a bit basic. I love the skull of Allosaurus fragilis. I think it's an absolutely amazingly gorgeous piece of mechanical structure. And then I don't know, Alverosaurids are crazy weird. If you think T-Rex is goofy looking for his short little stumpy arms, wow, like take a look at Mononicus. Like they're completely ridiculous. But yeah, there's lots of them. And then of course, I mean, you can't not love giant dromaeosaurs, like Utah raptor, completely ridiculously terrifying. Like the curved claw on each foot that's just, no. Like go hang out with a cassowary and then multiply that by 10, just hard no.
All right. Heathen Wizard says, sorry if I'm unclear. I can see how there would be ontogenetic niche shift between wildly different sized animals, but it seems weird to see them between individuals that are close in size. You make an excellent point about not seeing in ornithischians versus theropods. That does answer why we wouldn't see it in the herbivores.
Okay, I'm not clear on, so we do see ontogenetic niche shift in animals of similar size. We wouldn't necessarily expect to see ontogenetic niche shift in small species because the small species are starting out relatively similar in size as infants as they are as adults, right? So ontogenetic niche shift really applies to animals that are born small and grow to giant size. It's not necessarily a difference between species to species. So we see ONS in Albertosaurus, Daspletosaurus, Gorgosaurus, Tyrannosaurus, all of the Tyrannosaurids. We also see it potentially in Allosaurus, Carcharodontosaurus. Lots of very large megatheropods seem to have this, right? So it's not relegated just to Tyrannosaurs. It's not just in the Cretaceous. It is anything really that is getting up above the size of about 1,000 kilograms, but is born very small. I hope that clarifies a little bit.
Yeah, I hope that does too. And I'm not seeing any other questions come in. I'll give it another few seconds, but otherwise that will conclude our question period. We'd like to thank Kat for coming in to give us presentation today. We really enjoyed it. We learned a lot. And we'd like you to stay tuned to our social media accounts and our website for announcements on our next virtual speaker series, which will be coming out shortly. Thank you. And
all right. Thank you very much for having me.